So, welcome everybody to a new morning session of the School of Non-relativistic Quantum Field Theory, Gravity and Geometry. Our today's lecturer is Ziqi from Nordita, and he will tell us about aspects of non-relativistic strings. So Ziqi, when you're ready, you can start.
Thanks a lot, Diego. And I would like to start with thanking all the organizers for their hard work and bringing us together at this really wonderful summer school. So as the title shows, my responsibility is to explain something about non-relativistic string theory. So this type of theory arises as a corner embedded in the full relativistic string theory. And it's called non-relativistic because this type of string theory has a spectrum. It's a string spectrum that enjoins a Galilean invariant dispersion relation. So here I'm just giving you maybe ambitious outline that I don't have to finish everything. And I won't assume too much knowledge about string theory in case that there are people from the audience who haven't taken string theory officially. But I am going to borrow some concepts from string theory directly without duration. In that case, I'll just try to explain it in a conceptual way. And please do interrupt me when there's any confusion or I'm going too fast. But anyway, so let's start with some background information, and that also sets some motivation for our studies. So if we think about how we get relativistic physics from taking some limits of relativistic physics, the first thing that might come to mind might be this low energy limit, where we just send the momentum to be very, very small, especially compared to the rest mass of the particle. In that case, you can just expand the relativistic dispersion relation such that at the end, if you identify the effective dispersion relation, it's quadratic, Galilean invariant. So that describes as the Newtonian physics, which is perfectly designed for describing the macroscopic world around us. However, there's an almost opposite limit that we can consider, where you also see some kind of relativistic behavior. So this is when we consider the so-called infinite monotone frame, sometimes also under the name infinitely boosted frame or light cone frame. You'll see why these names pop up. So what do? We just choose one spatial direction and we take a large boost in this direction. It's so large such that all the particles are moving in the same direction. And then we want to boost it more such that at the end, almost all the particles are moving almost at the speed of light. So in practice, we just need to take this momentum along the direction we're boosting, and we send this momentum to be infinite. So here I denote this momentum to be Q and the transverse momentum to be K mu. And then you can just expand the relativistic dispersion relation again with respect to a very large Q. And at the end, we can identify states with finite energy, where we have this effective energy that we call epsilon. And if you plug this back in here, we'll see that the effective dispersion relation turns out to be, again, Galilean invariant. So this is generally speaking relativistic. However, if you think about what we really did, we just chose a particular frame to describe relativity. So even though this looks relativistic, but it actually describes you the full relativistic physics. And if you're able to undo the infinite boost, somehow you'll get back to the covariant formalism. So you might be wondering why we even want to consider this. So this type of method of describing physics in this infinite momentum frame has been quite powerful in terms of generating no-perturbative approaches in both field theory and in string theory. So because our focus is on string theory here, I won't talk much about the field theoretical stories, which has more or less the applications to QCD. But on the string theory side, this type of thinking has led us to the very famous matrix theory conjecture, which I'll review here because it's kind of relevant to our later studies. So now let's start with M theory, which is defining 11 dimensions. And we take this 11th dimensional spatial direction. And we compactify it over a circle of radius R11. And if you shrink this circle to be very, very small, then we're basically doing Kaluza-Klein reduction, which will lead us to string theory. And in particular, this procedure leads us to the so-called type 2A string theory. And you might ask the question, what are these Kaluza-Klein states corresponding to on the string theory side? So along this circle in the M theory, we have states with a quantized momentum that we call Q11, and N is an integer number. On the string theory side, these states correspond to some bound state of D0 branes. And indeed, if you calculate the mass, which is the brane tension of this D0 brane, it turns out to be proportional to 1 over G string. So if you're in this perturbative string theory regime, where G string is very, very small, then D0 brane is massive, like very much massive. That means this is kind of like a no perturbative object. However, if you try to probe the strongly coupled regime in type 2A string theory, that means we want to send G string to be very large, then D0 brane will have a very small mass, and therefore they'll become light excitations. On the other side of the M theory, we see that R11, the radius of the compactified circle, is proportional to G string. So with the large G string, we have a large radius of this 11th dimension. And that means if you send G string to be infinite, we have an infinite radius, and we're basically in this decompactification limit of M theory, and eventually we'll get to see this 11th dimension. So that means large G string leads us to the M theory regime. Okay, so now if we apply this infinite boost that we just talked about and describe M theory in this infinite momentum frame, something interesting happens. It turns out that we have a very unique dispersion relation that we talked about, which is non-relativistic. And there are very few objects which satisfy this dispersion relation. And these objects are exactly now lightly excited D0 branes. They have very small mass in the strongly coupled regime. And if you try to add in any other excitations, like some closed strings or open strings ending on the D0 branes, they'll mess up this dispersion. Oh, I'm sorry. They'll mess up this dispersion relation, and that basically means you haven't boosted enough. So here comes the punchline. M theory in infinite momentum frame is described by the effective field theory of these light D0 branes. So what is this type of effective field theory? That's very simple, because D0 branes are basically just particles, and therefore the effective field theory is described by this so-called matrix quantum mechanics. So this matrix theory conjecture says that M theory in this infinite momentum frame, it's just a particular choice of frame, is described fully by this matrix quantum mechanics. So this is something that's quite remarkable and has led to a lot of fruitful results. And you can apply the similar idea to string theory. And now, instead of taking this decompactification limit, we want to keep this compactified circle to be finite. So that leads to the idea of DLCQ of string theory. And DLCQ is short for discrete Lycon quantization. So there are multiple reasons why we are interested in this type of theory. First of all, this type of theory can be derived from a DLCQ of M theory compactified on additional spatial circle. So that's good for studying compactifications in M theory. And moreover, you can use this type of theories to engineer for some interesting ideas, CFT correspondence, for example, the famous PP wave correspondence, where you have a PP wave geometry in the bulk with or without compactification in the circle. And on the boundary, you have some type of spin chain system, the integrable, and under the name of BMN states. But in this talk, I won't mention too much about this side of the story, but you're definitely encouraged to read about them. And here I will be focusing on more formal aspects of the DLCQ of string theory, which will lead us to the idea of the so-called relativistic string theory. And we'll see that it's actually connecting many different corners in string theory. So now let's take string theory that's in 10 dimensions. And we want to take a spatial direction and compactify it over a circle of radius that we call R0. And then we want to take a large boost in this x1 direction. So we call the spatial direction to be x1. But you might think that this doesn't make sense because we already compactify x1 over a circle. So in some sense, we're already breaking Lorentz symmetry. But sketchily speaking, we can always take this circle to be very, very large. And then our local patch is almost flat. So we can still perform this large boost. So what do we mean by this large boost is that we send the speed of all strings to the speed of light. That says we want to send v to 1, which means gamma goes to infinity. But then if you look at the standard Lorentz boost, it seems that it's completely singular. However, if you take the trick and describe the physics in these light-cone coordinates, it turns out that we can define this so-called double scaling limit. While we're sending gamma to infinity, we also keep R0, the radius of the compactified circle, to be very, very small. This actually makes sense because when you take a Lorentz boost in x1, there's a length contraction, so the circle shrinks to 0 eventually. In addition, we want to fix the combination of gamma and R0 to be finite. So after going through a few lines of algebras, which I will leave you as an exercise, you'll see that eventually you can identify the original boundary condition with this new boundary condition, which defines as a light-like circle. So this is the light-like coordinate x plus compactified of a circle of radius r. And you can apply the same limit to the string spectrum for this dispersion relation. And as a result, we see that again, we get this Galilean invariant dispersion relation, which is quadratic in the transverse momentum. And there's one funny thing here. If you look at the original, well, here I'm writing down the closed string dispersion relation. And if you look at the original dispersion relation that we started with, there's a symmetry between the momentum number in x1, which is the Kaluza-Klein number, and the winding number in x1. So if you swap these two and also swapping the radius, then the dispersion relation does not change. So this is called P-duality, which is short for Target space duality in string theory. However, if you look at this resulting dispersion relation, we only see n, which is the momentum number in x1, appearing in the denominator of the dispersion relation. And the winding number only enters the dispersion relation via this level matching condition. So here n tilde and n are string excitations coming from oscillating modes. So this means we're kind of breaking a bit this T-duality symmetry, but that also indicates if we try to perform a T-duality transformation along this light-like circle, we should land on some different looking theory. So that's what we're going to do. And there's actually another motivation for doing this. In addition, that it looks interesting, which is that physics in a space-time with this light-like compactification usually turns out to be quite exotic, and it's kind of hard to decode what it means. However, because the dispersion relation that we found is just the usual Galilean invariant thing, so you might think that if you somehow take the T-dual along this light-like circle, maybe we can have a more first principles approach that such that we can just use mundane relativistic intuition to describe this type of DLCQ of string theory. So this is what we're going to do. We're going to compactify this x plus, which is the light-like direction, over a circle of radius r. So here I'm giving you the sigma model that describes relativistic string in this light-like compactification. And we have X mu, which are the worldsheet fields that map from the worldsheet sigma to spacetime. And because of this light-like compactification, we have a natural foliation structure induced in spacetime. And we'll call XA being the longitudinal sector and XA prime the transverse sector. So note that A, the index A goes from 0 to 1 and A prime goes from 2 to 9. And now we want to perform a T-duality transformation along X plus. To do that, well, note that T-duality is nothing but a canonical transformation, especially if you don't have the dilaton field. And that's just a standard thing that you would do in classical mechanics. So all we need to do is to come up with a generating function that takes this form. And I have introduced a Lagrange multiplier X tilde. And if you integrate out this guy, that will lead us to a constraint setting this guy to 0. And if you apply Poincaré's lemma on a local patch, you'll see that this new field V alpha can be solved by a derivative acting on some scalar. And if you identify that scalar with X plus and plug this back in, so the last term goes away, that's just used to impose us the constraint. So you just need to plug this guy back in here. That will lead us back to the original relativistic string theory sigma model. But instead, if we want to pass on to the T-dual side, we want to integrate out V alpha instead of X tilde. So if you do that, then it seems that we're just left with a quote singular action. We only get to see the transverse part. But however, note that the original action is linear in V, and that means V actually plays a role of Lagrange multiplier, which imposes as this set of constraints. So I've defined the derivatives with respect to light cone coordinates on the worldsheet. That's why we have this partial and partial bar. And if you identify X minus with the time direction on the T-dual side, and X tilde with a spatial direction on the T-dual side, you'll see that the first thing in the parentheses and also this guy in the parentheses are nothing but the light cone coordinates of the longitudinal coordinates in the T-dual theory. So you can, at the end, incorporate this set of constraints into the action principle by introducing a set of Lagrange multipliers that we call lambda bar. And this is the defining action for what we call relativistic string theory. So we're going to study this carefully through the whole lectures. But before that, I also want to point out, instead of getting relativistic string theory from the DLCQ of relativistic string theory, we can also find the same action by taking a low energy limit. And for historical reason, this type of limit is known as no commutative open string limit. I guess I'm going to elaborate on that later, but we don't need to care about the name for now. So what we do now is that we start with relativistic string theory, but in some background fields. So I have the metric field and the Kaplan-Meier field. So the Kaplan-Meier field is just a two-form gauge field, and it transforms under a two-form U1 gauge symmetry. And the action is actually invariant under this guy up to some total derivatives. And now if we choose some particular background field configuration, in particular, we have a electric part of the B field. And then if we plug this back in the action, we can rewrite it in this form. When we say that we want to take a low energy limit, we actually mean that we want to take the rigid slope alpha prime, which is the inverse of the string tension, to 0. But however, if you send alpha prime to 0 directly here, it blows up. But in contrast, if you integrate in a set of auxiliary fields that I call lambda bar, it turns out that all the alpha prime dependence is lumped into the last term, and the alpha prime only shows up in the numerator. So now you can safely send it to 0, which just kills the last term. So this leaves us again what we call relativistic string theory. And I define here alpha prime effective as the effective low energy rigid slope. So that's actually the rigid slope for non-relativistic string theory. But later on in the lectures, I will drop this index. Okay, here's just a summary. We can start with string theory in DLCQ and take the T-dual along this light-like circle. Even though it looks very singular thing to do, but actually we find a no singular result. That's what we call relativistic string theory, and it has a compactified spatial circle. And alternatively, you can also derive the same theory from a low energy limit of string theory, but now you need to couple the string theory to some critical background field. And finally, we can move on to take to some basics of relativistic string theory. So going to take seriously this action and really try to understand what it means. And we'll start with the closed string sector. So I already explained that this lambda and lambda bar are just Lagrange multipliers, which impose some constraints, and you can think about them as holomorphic and anti-holomorphic constraints by setting these guys to 0. And in space-time, because of the presence of this lambda bar, we have this foliation into a longitudinal sector with index A goes from 0 to 1, and the transverse sector with the index A prime going from 2 to 9. And we also need to keep the spatial direction x1 to be compactified over a circle of radius r, for the reason I'm going to elaborate later. The first thing to notice is that this action has a relativistic global isometry in the target space, which means this action is invariant under this global symmetry. And you can, well, if you identify xa as the time direction and xa prime as the spatial directions, then this is nothing but the Galilei boost, but now with the generalization to the two-dimensional foliation structure. And for that reason, we call such a boost symmetry a string Galilei boost. So here we have natural interpretations of x mu as the space-time coordinates in the target space, but you might wonder whether there's some physical meaning for this lambda and lambda bar. And indeed, if you go back to these T-duality transformations and perform both T-duality transformations in x1 and also in the time direction, but you might complain that it doesn't make sense to apply a T-duality transformation in the x0 direction, but you can always weak rotate it and compactify over a circle that defines your string theory at the final temperature. And in that case, you can perfectly perform a T-duality transformation also in the time direction. But at the end, you can read from these type of transformations that lambda and lambda bar are related to derivatives acting on the T-dual coordinates that we call y. So ya is T-dual to xa. So in this sense, lambda bar actually the one-form fields which already know about the T-dual frame. So in this sense, xa is actually conjugate to the string momentum, while ya is conjugate to string windings. But now we're going to forget about this T-duality interpretation, but just take these equations as a set of redefinitions of the fields lambda and lambda bar. But there's a caveat here. If you directly plug this set of redefinitions back into the action principle, you'll see that because we have time derivatives acting on the y field, and therefore, if you directly put in the path integral, you generate some additional degrees of freedom that you don't want. So you have to couple it to some ghost degrees of freedom. But instead of doing that, we're still going to work directly with this action without these redefinitions. But why am I doing this? Because this is actually a very useful redefinition that you can introduce when you try to compute, for example, the string amplitude. If you just do this at the operator in the operator formalism, then there's nothing wrong with it. Okay, so now let's see why these redefinitions could be useful. So now we want to consider the operator product expansions, and we take, well, the transverse. This transverse product is nothing but the same as in relativistic string theory, so it will just give you the normal OPEs. And by the way, the OPs are basically giving us the propagators in position space. And if you take now the contraction between the one form field lambda and, for example, X, we get this 1 over Z. However, if you plug in our redefinitions, we'll see that there's a contraction between the dual coordinate Y and X, which gives us the standard looking OPE, that's log Z. So already introduced radial quantizations. I'm working with these complex variables that we call Z, and also Z bar, of course. So because this form already looks very similar to the OPEs in relativistic string theory, and therefore we're motivated to introduce a set of new variables that actually mixed up the coordinates X and X bar together with the T-dual coordinates Y and Y bar. So as you can see, X is holomorphic because of the constraint imposed by the Lagrange multiplier lambda. And therefore X only depends on Z. And similarly, X bar only depends on Z bar. And actually, you can also show that Y only depends on Z. And therefore, whenever I write phi L, that only depends on Z. So that's completely holomorphic. And you can do similar thing to the transverse coordinates. And that's a standard thing to do. You split it into the left moving and right moving part. So the left moving part only depends on Z. The right moving part only depends on Z bar. And now, magically, in this new set of variables, if you now compute the derived OPEs, they look exactly the same as in relativistic string theory. So this actually gives rise to a very nice trick that we can pull out. This means if you want to, for example, compute some OPEs and therefore some string amplitudes in this relativistic string theory, we just need to borrow the same result from relativistic string theory, but then plug in this set of redefinitions of fields. And they'll automatically produce us the desired results in relativistic string theory. Okay, but the physical interpretation is completely different because now you see that all the fields mix up different size of T-duality. And you can also see that the stress energy tensor takes the same form as in relativistic string theory, again with a very different physical interpretation. And therefore the BRST quantization structure does not change at all. And you can conclude immediately that we do have the same critical dimensions. That means superstrings live in 10 dimensions and the bosonic string theory lives in 26 dimensions. So this also applies to our non-relativistic string theory. And now finally, we can identify some physical states in the relativistic string theory. But before that, let me first review a little bit what we do in relativistic string theory. So there's one novelty here, even in the relativistic side. We introduced these left moving and right moving modes and they're treated differently. And that means in general, we need to consider string theory with some compactifications. And how does that go? So let's take this example in relativistic string theory where we compactify a single spatial direction over a circle of radius r. But you can also do more, but this won't change anything conceptually. So I want to take the mode expansion where we have sigma 2 being the worldsheet spatial direction and sigma 1 being the worldsheet time direction. So the third term here has a winding number W. That means if you go around the worldsheet spatial circle for one time, you're actually going around the compactified circle in space-time for W times. And in front of the time direction, we just have the momentum number in X. And now you can split X into XL and XR, which are the left moving and right moving modes. So the left moving part only depends on Z in the radial coordinate, and XR only depends on Z bar. So in this sense, we can introduce the left moving momentum that we call KL and the right moving momentum that we call KR, which are only different from each other when you have a non-zero winding number. So finally, we can cook up this so-called vertex operator, which is a local operator that we can insert on the worldsheet topology. And you can always map an asymptotic string state to a local vertex operator because we have conformal symmetry on the bullshit. So the vertex operator is nothing but a plane wave, but involves both XL and XR, and also with the left moving and right moving momenta. We can apply the same idea to non-relativistic string theory. So just introduce this plane wave looking guy. And in addition, we have a T-dual coordinate YA, and the coefficient in front of it encodes the winding number. So this vertex operator represents the closed string tachyon in relativistic string theory with the list of quantum numbers here. And now if we plug in the redefinitions from XY to phi L, phi R that we defined earlier, you'll see that we can rewrite this vertex operator in the same form as we constructed for the closed string tachyon vertex operator in relativistic string theory. Except that you have to map this kinematic data to this KL and KR, and they take a very different form. However, mathematically, you can still go ahead and compute the BSD invariance of this guy, which means that the vertex operator is made to be conformal at the quantum level. And that leads to the standard relativistic string dispersion relation. But then upon plugging this set of new variables for KL and KR, we can get this relativistic dispersion relation. So this is for tachyons, so we have a rather trivial level matching condition. But you can generalize it directly to more general closed string vertex operators by decorating this tachyon vertex operator with some directive terms. So that'll give us this fully general dispersion relation for closed strings. And with these vertex operators in hand, we can finally compute some physical state, physical observables. For example, for the simplest case, but still no trivial, this 4 tachyon scattering process. So here we have asymptotic closed string states carrying both winding and momentum. But for tachyons, you can only carry one of them because of the level matching condition. But we do this calculation bearing in mind that we also include all sorts of higher order vertex operators. So you can now have like 2 closed string states coming in, and they merge into a single intermediate closed string, and then this intermediate state splits into 2 outgoing closed string states. And by applying a conformal mapping, you can shrink all these asymptotic closed string states to some insertions of local vertex operators on this sphere. So, and then you can apply this Mobius transformation, which is SL2C transformation. Oh, I'm sorry. To fix 3 locations of the vertex operators. And at the end, we just need to integrate over the complex plane for the location of 1 vertex operator. And that gives rise to the standard Brasser-Shapiro amplitude. And the only difference is that the kinematic data has to take this form. So note that because we are doing the calculation for tachyons, in this special case, due to the level matching condition here, we have KL being equal to KR. That's why we only have 1 K here. And I just recall that there's one important thing that I forgot to point out. So if you look at this dispersion relation, it has a winding number in the denominator. And that means all the physical states in the Hilbert space will necessarily have to have some no-zero winding number. And therefore, we must have a compactified circle in order to have some propagating string states. And that's why in this case, n has to be set to 0 for the tachyon state, because W is not 0. But anyway, when everything is settled, we get this amplitude that's informed the same as in the relativistic case, but now it's actually the closed string amplitude for relativistic closed string theory. And it has the usual poles, which give you the intermediate closed string states with winding numbers. But if you look at it more carefully, there's also a very special sector. That's when you preserve the winding numbers through this scattering process. In that case, the intermediate closed string states won't carry any winding number. And if you look at the amplitude, if it will develop a kind of like a singular pole that's 1 over k squared. So k is only the transverse momentum. And this type of pole is basically represents a intermediate state that you cannot put on shell. But instead, this type of intermediate state mediates some instantaneous Newtonian-like interaction. And if you study the effective action of effective field theory giving rise by these vertex operators without winding number in the 0 winding sector, that will give rise to what we call the string Newton-Garton gravity. And you can also do.
Can
yes,
I
please.
ask a question? Yeah.
Of course, please.
Yeah. So if there is no compact dimension, are you saying the theory is completely trivial? Or there is no spectrum, or what is the precise statement for the all non-compact space?
That's an interesting question. I should have emphasized that. Thank you. So when you don't have any space-time compactifications in the longitudinal sector, then you will have kind of like a trivial closed string spectrum, which means that you don't have any propagating string states. But if you look at the open string part, as I will actually talk about very soon, you do have this no commutative open string sector, which is perfectly well defined. But it's just in that case, you cannot calculate to closed strings anymore. Is that clear?
Yeah, but the theory itself is consistent, even though that for closed string.
In which case, when you don't have a compactification?
Right, yeah.
Well, you just don't really have a closed string sector in that case.
Yeah, but there is no inconsistency about this. Yeah.
Yeah, you just don't have any propagating closed string states in the asymptotic limit. That's all I can say, I guess.
Okay, yeah. Thank you.
Thank you. Well, that's actually a very important point. But anyway, we can also do one loop amplitude calculation in this closed string sector. And I won't go through the details here, but I just want to note that the usual integral over the moduli space, for example, for one loop, you have to integrate over this fundamental domain in this SL to C symmetry group. But now, because of the holomorphic and anti-holomorphic constraints that I have in relativistic closed string theory, it turns out that this integral over the fundamental domain is localized to be a sum over a set of discrete points in the fundamental domain. And you can also see these type of localization theorems for higher loop amplitudes. And moreover, by doing this loop amplitude, we can see that this type of string theory is actually unitary and also free of any UV divergences. So after talking about closed string sector, but maybe I should pose for question because now I want to talk about open strings and also how much time actually I'm running out of time for lecture 1. So maybe I'll just stop here and we'll talk about open string sector in the next lecture.
Okay, that's a good idea. So, well, thank you so much for this great lecture. And well, time for questions.
Maybe I will stop recording so you can feel more free to ask questions.
Okay.
I just pause.
Okay. Welcome back, everybody. Now we continue with the second lecture of Ziqi Yan about aspects of non-relativistic strings. So Ziqi, it's your time. You can start.
Thank you, Diego. So we just talked about closed string sector in this relativistic string theory. Now we move on to the open string sector. And because we have a space-time foliation with this two-dimensional longitudinal sector being treated kind of like differently. So now, depending on what kind of boundary conditions that we put on the string worksheet boundary in this longitudinal sector, we have different open string sectors. So for simplicity, let's just assume that in all the transverse directions, we have Neumann boundary condition, which means that have derivative perpendicular to the wall sheet acting on xa prime being equal to 0 on the boundary. However, in the longitudinal sector, we can have different choices. If we say that we have Neumann boundary condition in the longitudinal sector, that means in both x0 and x1, we have this type of boundary condition. Then that leads us to the idea of no commutative open string theory. Well, when you have an electric field present, that leads to a no commutative relation between xa and xb. So in this sector of open string theory, we actually have a relativistic dispersion relation. So this type of theory has been studied quite a lot around 2000. I won't talk too much about it, but we'll also come back to this type of construction later when we talk about curved spacetime and effective field theory on D-branes. However, if we now say that we take a Dirichlet boundary condition in this compactified circle x1, something different happens. We actually get the so-called non-relativistic open string. I'll call it an ROS for short. So in addition to these Dirichlet and Neumann boundary conditions, if you vary the action and require to be 0, then we also get additional boundary condition, which basically says the lambda bar becomes the same thing on the boundary. In this case, you can see that the global symmetry is now broken into basically a Bargmann symmetry on the D-brane. So we have the standard Galilei boost on the D-brane. And now we can again insert vertex operators on the boundary of this wall sheet topology by turning on some vertex operators for gauge fields. So here I'm focusing on the sector without winding numbers. So again, we have some intermediate states that mediate electromagnetic type of forces between winding strings. So most general form of the vertex operator takes this one. And here we have A0 and AA prime being the gauge potentials on the D-brane. We also have the Nambu-Goldstone boson N, which perturbs the shape of the D-brane in the compactified X1 direction. And you can show that this vertex operator is invariant under this boost symmetry, which is actually the Galilei boost. And that's, if you still recall what Shira talked about yesterday, that's exactly what she presented in her last lecture for this theory of Galilean electrodynamics. And indeed, if you work out the self-consistency equations for this vertex operator by requiring that this is conformal at quantum level, so you have these BLST invariance conditions that gives rise to the equations of motion for different fields. And it turns out that this set of equations can be assembled into an action principle, which is exactly Galilean electrodynamics. And please see Shira's lecture if you don't remember. And I won't go through the details of it. And I'll just note that this theory does not have any propagating degrees of freedom because, well, from the string theory side, we are in the zero winding sector. And we know that all physical states will necessarily have to have no zero winding number. So indeed, if you turn on windings, we have this standard Galilei invariant dispersion relation. And moreover, the mysterious scalar field that Shira talked about now gains a geometric interpretation. It is the Nambu-Goldstone boson, which presents because we insert the D-brane localized in this compactified X1 direction, which breaks the translational symmetry in X1. And that's why we have this massless excitation that perturbs the shape of the D-brane in X1. And you can directly generalize this to the Yang-Mills case by considering a stack of coinciding D-branes. So in this case, the vertex operator has to be replaced by Wilson line coupled to some adjoint scalar N. And we have to take this path ordering and then take the trace, but you can again evaluate the BLST conditions on this vertex operator. well, it's not really a vertex operator anymore. It's more like a Wilson line, I guess. And at the lowest order in the field strength, we'll find this Galilean-Yang-Mills theory. That's a direct generalization of Galilean electrodynamics. Okay, so this is a summary for the relations between NCOS and NROS, which I will elaborate more later, but I just want to mention, like in one sentence, that there's actually a T-duality relation between these different open string sector. Okay, but now we can go back to our string amplitude analysis, and it's pretty much straightforward. We can do exactly the same thing as we did for the closed string amplitudes. And now here we get the Veneziano amplitude for these tachyon vertex operators, but now for open strings. So at the end, you can see this is just the Euler's beta function. But again, the difference here in comparison to relativistic string theory is that we now have a different kinematic data. So the winding for open string comes from that we take one open string and fix the ends of the open string on the same d-brane. By the way, in this case, I'm only talking about non-relativistic open string theory. We won't talk much about no commutative open string theory. So at this point, we have computed some string amplitudes, the physical observables in relativistic string theory. And now in the next part, I would like to see whether there's some deeper structure that relates closed string and open string amplitudes. So in short, we want to find a generalization of the standard KLT factorization of closed string amplitudes into open string amplitudes, but now to in the domain of relativistic string theory. So let me first tell you about what is KLT factorization in relativistic string theory is about. So in the standard relativistic string theory, without any space-time compactifications, there's this very famous relation found by this gentleman back in 1985. That's called the KLT factorization. And it happens at the tree level, and it's actually still an active field to study for the generalization of these to loop level. It's not certain whether this kind of factorization still holds at loop level. But if you apply this same idea to the field theory limit, that inspired this idea of gravity equals Yang-Mills squared, which has also generated many different works since then. For example, this double copy construction and the BCJ relations. So that has led to very fruitful results in field theory amplitude calculation. It turns out to be quite powerful and enables you to calculate higher loop amplitudes in gravity. But here I will be focusing on the string side. So in string theory, what is the KLT factorization? That is when we take a closed string amplitude at tree level. So let's say we have a 4-point amplitude with 4 vertex operators inserted on a sphere. So this amplitude is defined by complex integral over the full complex plane. And intuitively, this complex integral splits into a quadratic product of contour integrals. And such contour integrals will represent some open string amplitudes. And therefore, the closed string amplitude factorized into a quadratic product of open string amplitudes. And at the middle, we have this Monotone kernel, which is basically a phase factor. So let's see how this works out in a specific example. Let's again take tachyon operators just for simplicity. And we also define these Mandelstam variables where we have STU, which are related to kinematic data. We also define this alpha, which is a function of this kinematic data. Okay, so if you compute, well, basically we already wrote down the integral for this closed string amplitude. And if you actually evaluate it, we get this expression. And quite trivially, you can rewrite it in this form. And you can identify this guy and that guy as Euler's beta functions. which can be then interpreted as open string amplitudes. At the middle, we have these gamma functions, which can be rewritten in terms of a sine function. So that's basically a sum of phases. And this expression matches exactly what we have here. Okay. Usually in this KLT relation, the open strings are defined on some space-time filling debrains, which means that we have Neumann boundary conditions in all directions. And now we want to generalize the same idea to non-relativistic string theory, but quickly you'll realize that many things haven't really been done. For example, in non-relativistic string theory, as I have mentioned, we have to have a compactified spatial circle. But for some reason, no one really studied the KLT relation in relativistic string theory, but in some space-time compactification until very recently in our paper. So let's see how this goes. So we're still in the domain of relativistic string theory. And we want to consider the KLT relations for winding string amplitudes. So now we consider asymptotic closed string states that carry both winding and momentum. And again, we'll be focusing mostly on the tachyon states, in which case Wn is set to 0, but we're bearing in mind that we also apply this type of construction to higher order vertex operators. So in general, we can indeed have both winding and momentum in the compactified circle. So this is the same construction that I introduced earlier, and you can have this vertex operator. And now the closed string amplitude still splits in the similar way, except that we'll have to introduce these generalized Mendelssohn variables, and we just address everything up with left and right moving labels, and that's because we have left and right moving momenta. So now we found this splitting where we have these different Euler's beta functions, and also the phase factor here. But quickly you'll see that there arises a puzzle. The question is which amplitudes, which open string amplitudes these Euler's beta functions correspond to. If you think about it, it's a little bit strange because on the closed string side, it's perfectly fine for incoming or outgoing closed string state to carry both momentum and winding in the compactified direction. But this is not true for open strings. An open string can only carry either momentum or winding, but not both. So if you look at different boundary conditions that the open string satisfy, we'll easily see why this is the case. So if we start with an open string that satisfies Neumann and Neumann boundary conditions on both ends, which means that neither of the ends is fixed, and therefore you cannot really wind the open string around the compactified circle. But you can indeed have some collective momentum. The open string can move in some particular direction. And instead, if you have Dirichlet boundary condition, then let's say we'll have a single debrane localized in this compactified x1 direction, then you can take one end of the open string anchored on this debrane, and then wrap the open string around the compactified circle for W times. So you have a winding number W, and finally you join the other end of the open string to the same debrane. But in this case, you just cannot have any collective momentum. And finally, we can have this mixed boundary condition with Neumann and on one side and Dirichlet on the other side of the open string. In this case, it just kills both momentum and winding. So I guess depending on, well, first of all, it doesn't seem that the last scenario is useful because it just kills everything. But for the first two pictures, they're just due to each other. So depending on your taste, whether you like KFT more or you like a more geometric point of view, you can just choose one of them, and then you can take the T duality to get the other side. So here I would prefer to work with this more geometric interpretation when I have Dirichlet and Dirichlet boundary conditions on the ends of the open string. And as a result, we can just draw pictures. So here we can easily map the closed string winding number to the open string winding number. So this is an integer winding number. But then the question is, how can we accommodate the closed string momentum number? To do this, apparently we have to introduce some extra structures. It turns out to be quite simple. Instead of considering a single D-brain, we just now need multiple D-brains localized along this compactified X1 circle. Of course, you can take the T2 and consider Wilson loops in the dual picture instead of multiple D-brains. So let's see how this works for a very specific example. So I have two incoming closed string states on the left-hand side of the KLT relation. Well, for the first closed string, we have momentum number being equal to 1 and the winding number equals whatever. Because we know the winding number of the closed string is just mapped to the integer winding number of the open string. So that part we understand. And then the second closed string will have a momentum number 3. And of course, in this scattering, the momentum number, momentum numbers just conserve. Then on the open string side, let's design this D-brain configuration such that this momentum number of closed string scattering is encoded in this D-brain configuration. So now along this compactified X1 circle, we take n plus 1 D-brains. So how do we define this n plus? That's just the total incoming closed string momentum numbers. So that's equal to 1 plus 3, and then we add 1. So in total, we have 5 D-brains. And we separate these D-brains localized in X1 such that the separation between each two consecutive D-brains is equal to 2 pi alpha prime over r. So this distance is due to the circumference of the compactified circle of X1. And now for the first open string, which corresponds to the first closed string, we recall that this open string is stretched between the first and the second D-brains. So in addition, you can also wind around for W times around the whole X1 circle. So this, the fact that the open string ends on 2 different D-brains gives rise to a fractional winding number. And you can do the same for the second D-brain, for the second open string, and we'll let it to be stretched between the second and the fifth D-brains. So you can see the number of the gaps that the open string stretches are mapped to the closed string momentum numbers. In this sense, we have these closed string momentum numbers being encoded in the fractional winding numbers of the open strings. And the conservation law of these closed string momenta is now realized by open strings splitting and drawing on the D-brains. So this is a very simple picture, but after doing this, you can indeed establish a simple KLT relation for winding string amplitudes. But in order to make contact to our non-relativistic string theory, we know that for one, we need one compactified circle in the spatial direction. But then if we want to get non-relativistic string theory from this low energy limit by sending alpha prime to 0 in relativistic string theory, as I explained earlier, we also need some background Capra-Mon field. And again, KLT relation in background field was not really explored that much in the literature. So now, in order to make contact to relativistic string theory, we also need to introduce some new ingredient to the relativistic KLT relation. So I want to study KLT relation in electric B field. So on the closed string side is very simple. The fact that we have a B field lying along this longitudinal direction just says that we have a shift that's proportional to the B field of the energy. Also, this shift is proportional to the winding. So you must have a compactified circle in order to have a no zero term here. But on the open string side, there seems to be a problem again, because on the open string side, in order to accommodate these closed string momentum numbers such that we can match this second entry in the kinematic data, we had to introduce some fractional binding that's just imposed on us. So in the presence of this B field, the energy of the open string will be shifted by a quantity that's proportional to the total winding number, including this fractional binding. So as a result, we see that we have an additional term in the energy entry on the open string side. Again, there's a mismatch. And the solution is again quite simple. We just need to introduce some gauge potential. It's actually some electric potentials on each D brane. And this electric potential has to take a very specific form. And once you take this into account, you only shift the energy on the open string side. So you can tweak this particular value of the electric potentials such that this additional contribution in the energy shift is canceled. So finally, we can indeed have a KLT relation in relativistic string theory in the presence of space-time compactifications and also in the presence of this electric B field. And at the end, we can take this alpha prime goes to 0 limit. Of course, you can also construct from scratch just using the ingredients that I told you about for string amplitudes in relativistic string theory. So at the end, we can construct this KLT relation in the relativistic string theory. Because we want to take this alpha prime goes to 0 limit, that means the separation between the D branes is now shrank to 0. So instead of having this array of D branes separated by the same distance, we now, in the relativistic string theory, have a stack of D branes. But the gauge potentials are still the same. Actually, you'll see that this is still proportional to alpha prime, but you have to rescale the gauge potential in order to get this relativistic string theory. So at the end, you still have the same type of gauge potential on a stack of D branes. So it seems that you have a UN Young-Wilson theory, but because we chose the gauge potentials to be purely electric and also they're constant, so this UN group is broken into its Gathon subalgebra, so that we only have U1 to n plus plus 1 as the symmetry. So n plus plus 1 is the total number of the D branes. And you can directly check that indeed you get a matching kinematic data on both sides of the KLT relation in this relativistic string theory. But this is, well, I've been sketchy about one additional factor here. So when you have winding strings, you also have these so-called co-cycle factors, which you have to insert as a phase factor to ensure that you can commute vertex operators. So you don't get no physical branch cuts. So these co-cycle factors also play a non-trivial role in this KLT relation, but I won't go through it. But if you're interested, you can look up our paper. Okay, so I'm going to switch to a different topic. So maybe I should stop for questions, if you have any. So either I got all of you confused or everything is too simple that I cannot tell. But no, in any case,
you should continue.
Okay. I hope it's not too much for you. But anyway, so I'm going to talk about a different topic now. So in the previous lecture and also the first part of this lecture, I went through some quote unquote basics, but mostly just string amplitudes in relativistic string theory. I hope that you have a better understanding of what this theory is about. And now I would like to ask a different question. Well, but it's also very relevant. We want to understand now what is our string theory about? What kind of effective field theories it gives rise in space-time, in the target space. So we start with the closed string sector. In this case, we would like to answer the question, what kind of gravity theory that our relativistic string theory gives rise to in the target space. So this will give rise to the idea of string Newton-Raphson geometry and string Newton-Raphson gravity, as Yang mentioned in his lectures. And after this, you can establish the notion of non-relativistic quantum gravity, so that non-relativistic string theory is basically a quantum gravity theory of this string Newton-Raphson gravity. Okay, so let's again start with our action that we have been working with in flat space-time. And now we want to insert vertex operators and actually want to exponentiate such vertex operators so we can consider the coherent states of closed strings, which will give rise to the curved background as an emergent concept. And in practice, we just need to include all possible marginal interactions in this sigma model. So we have an interacting nonlinear sigma model. And we'll start this process by first undoing the conformal gauge that we have been taking so far implicitly. By doing that, we can define our theory on a dynamical wall sheet, and therefore we will be able to couple a dilaton field to it, which will give rise to the string coupling. So I want to introduce the wall sheet metric field together with the Dwight bind field. And then we also want to go to the light cone coordinates in the tangent space on the wall sheet. So using these ingredients, you can easily covariantize all these derivatives on the wall sheet, and you have a more ugly looking expression. But if you look more carefully, the first two terms and the last term are just informed the same as in relativistic string theory. So already turn on arbitrary background fields that we call H, B, tau, and phi. And there's also this U, which I will explain later. So phi is the dilaton field, and well, these background fields are nothing but just some Taylor expansion with respect to X. And because X is dimensionless, so in this two-dimensional sigma model, you can introduce arbitrary polynomial in X, and they're still marginal operators. And B is the antisymmetric Cabral-Ramon field, and H mu seems to be a metric field, but I will show later is actually not qualified as a metric field. In addition, we have this tau mu and tau mu bar, which play the role of longitudinal Wurlbine field, as we will see later. So, and in addition, we have this actual operator, which we don't see in the flat theory. So this operator is perfectly consistent with the conformal symmetry. But before I proceed, I would like to introduce these curly D and curly D bar variables, such that we can write the action in a cleaner form. So this is the action that we're going to work with through the rest of the lecture. Now let's focus on this strange looking term, lambda bar with a coupling U. Whenever U is not zero, you can always integrate out lambda and lambda bar, which surprisingly, or maybe not too surprisingly, will give us this relativistic string sigma model in curved background fields with G, B, and phi taking this form. So whenever I have a hatted notation, that means we're in the relativistic region. So this is a bit disappointing, I guess, because we claimed earlier that we want to study this limit of relativistic string theory, which is self-contained. And we want to call it relativistic string theory because it has a relativistic string spectrum. But however, it seems that when we turn on arbitrary interactions, we're led back to the full relativistic string theory. So what do you mean by relativistic string theory even? But if you really think about it, this is not surprising at all. I mentioned at the beginning of the last lecture that this relativistic string theory in flat space-time is just Q-dual to the DLCQ of string theory. And what is DLCQ? That's just a particular frame that you choose to describe relativistic physics. So in principle, if you are able to turn on all interactions in this string theory, you should be getting back to the full relativistic string theory. And indeed, the sigma model that we wrote down here is nothing but relativistic string theory expanded around the non-relativistic vacuum defined by this flat action. Okay, and you can also see that this lambda bar is indeed a deformation that takes us away towards the full relativistic string theory by looking at the dispersion relation. So due to the presence of this lambda bar term, we have a constant U0, and that will deform our non-relativistic dispersion relation by that guy. And indeed, now you see that we now have a zero winding sector with a perfectly relativistic dispersion relation. So one way that we can do is that we can just send this U to 0. So we kill this lambda bar operator by hand. It seems to be fine. You can just do this at this conformal fixed point, which is required for the string theory to be defined anyway. But if you really think about it, we kind of already lost the notion of a self-contained corner for relativistic string theory. And this is because before going to the conformal fixed point, we need to first start with this sigma model and quantize it and study the RG flow of all these couplings. In that case, you'll see that this sigma model is not renormalizable. So if you turn on quantum corrections, you will see that this lambda bar will be generated by a log divergent quantum correction in the effective action. So this means we can only treat this action as embedded in the full relativistic string theory sigma model. Even though we tuned U, the coupling U, to 0, we can only set the physical coupling to 0, but we'll still have keep the counter term lambda bar around if we want to study the quantum mechanical behavior of this sigma model. And then if we go to the conformal fixed point, this coupling U will still give rise to a no-trivial beta function. So here comes a very natural question. Maybe we're just missing some extra symmetry principle. And by imposing these extra symmetry principles, maybe we can still protect a self-contained relativistic corner. So this is what we're going to do next. We're going to study string sigma models in the so-called string Newton-Gagnon geometries. In order to classify all symmetries that are available for us to build up this nonlinear sigma model, let's go back to the flat action again. So we want to classify the global isometries in space-time, which turns out to be infinite dimensional. But if you turn on interactions, usually you're breaking most of it. So here I'm only going to note that we have these standard isometries for translations in both longitudinal and transverse directions. And we have the longitudinal Lorentz boost, the transverse rotations. In addition, we have these so-called string Galilei boosts that relate to these longitudinal and transverse sectors. However, it turns out that this action is only invariant under our string Galilei boost up to some boundary term. And this means if you compute the conserved charges and then also the commutation relations between them, you should get some extra extensions of the algebra. So indeed, if you compute this particular commutation relation between the string Galilei boost and the transverse translations, we get a so-called no central extension ZA. It's no central because it has a longitudinal index A, which means it transforms no trivially under, well, which means it does not commute with the Lorentz boost generator M. And indeed, if you compute this conserved charge is related to the string winding and the string momentum in the x1 direction. And moreover, to maintain the closeness of the algebra, you have to introduce a second no central extension that we call Z, but it won't be playing much a role in the remaining of the lectures. So we're simply not going to talk too much about it. But anyway, if you collect all this data, you'll see that we have a so-called string Barkman algebra, which is a very natural generalization of the Barkman algebra for particles. So now we can just take this set of algebra and gauge it which will give rise to a gravity theory in space-time. I guess I don't need to explain too much about the gauging procedure. Yang already gave a perfect lecture elaborating many essential ingredients about it. So all we need to do is that we assign a gauge field to each generator. So for the translations, we have this longitudinal Wilbine within the longitudinal sector and transverse Wilbine within the leaves in the foliated spacetime. We also introduce a U1 gauge field that we call M mu A, which is a direct generalization of M mu in Newton-Garton gravity that's associated with this ZA symmetry. So it's easy to construct a theory that is invariant under the translations. We just need to carefully contract all the indices. And it's slightly more subtle to make sure that the action is invariant under the boost. But it turns out that we can construct two different variables which are boost invariant, and both of them will carry lower curved indices. And these are the quantities which we need in order to construct the sigma model, which is invariant under the so-called string Bachmann algebra. And here tau mu A is just trivially invariant, and H mu contains our M field. So it looks like this can be a metric field. Oh, by the way, I forgot to explain this. E mu nu is just a purely transverse part that's essentially E mu A prime times E mu A prime. But at first sight, it seems that H mu nu is a metric field, but it's actually not, because this guy is not invariant under this ZA transformation. And this is because in the next slide I will show M mu A transforms trivially under ZA. Okay, so this means we actually have a no Riemannian geometry in space-time. We don't have a metric field. So this is intrinsically no Lorentzian, of course. And then with these ingredients, you can easily construct an action invariant under everything except for this ZA symmetry. So this is informed the same as we constructed before by just inserting all possible marginal interactions, except that we set this lambda bar to 0. But we also said that this sigma model is not really renormalizable, and we wanted some extra symmetry to protect this lambda bar against any quantum corrections. And this symmetry turns out to be this ZA. Well, I have to note that this is not the only symmetry that we can use. Actually, this symmetry turns out to be a bit too restrictive. For example, if you want to generalize this to supergravity. Hopefully, I will have time to address this issue in tomorrow's, at the end of tomorrow's lecture, if we got time. But anyway, now let's analyze the invariance of this action under the ZA symmetry. It turns out that imposing this ZA symmetry and require the action to be invariant requires a additional condition acting on this longitudinal Wilbine field tau mu A. So this is what we call the zero torsion constraint. So D here is defined with respect to the spin connection in the longitudinal sector that we call omega mu. So this spin connection is associated with the longitudinal Lorentz boost. So part of this equation can be used to solve for this spin connection, but the remaining part give rise to some genuine geometric constraints. So this defines us the so-called string sigma model that describes non-relativistic strings in the so-called string Newton-Garton geometry, supplemented with this zero torsion constraint. And now we can revisit the renormalizability of the sigma model. So I won't go through the details here, but you can take it as an exercise by going through these lines after the lecture. So now we want to study the sigma model with this additional zero torsion constraint. It turns out that the contribution to this lambda bar term quantum mechanically come from the vertices that you can derive from these two operators. And if you, for example, compute the one loop Feynman diagram that gives rise to a contribution to the lambda bar operator, it takes this form. And indeed, it's proportional to this guy, which is automatically set to 0 when you impose these geometric constraints that come from the zero torsion constraint. And this behavior also survives for all higher loops. There's actually some non-relation theorems that we proved in these papers. Well, when you have such a zero torsion constraint, lambda bar is not generated at all. So you have renormalizability for the sigma model. And moreover, lambda mu A is not renormalized. So in this sense, we can have a self-contained notion of non-relativistic string theory, even though it might be too restrictive. But for now, we just focus on this simple case. So with all this being said, we can finally compute the renormalization group flows in this sigma model. And they'll give rise to the beta functionals for different couplings. Setting which to 0 will lead us to the conformal fixed point where the string theory is defined. And these vanishing beta functions will give rise to the space-time equations of motion that govern the dynamics of the property space geometry. But before doing that, we know that there's some redundancies in our parameterization. So we introduced this H mu nu field and also the Cabral-Mon field B mu nu. And this H mu nu contains the M mu A field coming from gauging the ZA symmetry. However, it turns out that there's some path integral identities that you can write down, essentially coming from the fact that I have a Lagrange multiplier lambda that imposes this basically holomorphic constraint, but now in curved background. So that sets this guy to 0 in the path integral. So that's a word identity. And that's actually associated with a very classical argument. It's coming from the fact that you can redefine the Lagrange multipliers lambda and lambda bar without changing the theory. So for example, if you shift lambda and lambda bar by this arbitrary function that we call C mu A, but now in the light coordinates, that will generate this type of shifts in H mu nu and B mu nu. And you can plug this back in, and you will see that the action is actually invariant. So now, well, this type of shifts basically means that you have some kind of redundancies in the parameterization, and they're similar to what they call the Stueckelberg symmetries. And now, in order to perform the quantum calculation, for example, we want to use the covariant background field method to compute the beta function nodes for these couplings, just like in standard sigma models. It's better if we fix these Stueckelberg symmetries by setting C mu A to be M mu A. So in that case, you got to kill this M dependence in H mu nu, and H mu nu is turned into E mu nu, which is purely transverse. But then B mu nu will gain some M dependence. So you get this capital M that depends on M mu A. So I have to note that M mu A transforms non-trivially, for example, under the string Galilei boost, and also under the ZA transformation. And therefore, M mu nu is very different from the normal notion of Cabral-Mon field. It's actually part of the full geometry. It transforms non-trivially under the string Galilei boost and the ZA symmetry. But now we don't have any, well, we still have a little bit more redundancy, but let's don't care about it for now, for the technicality. But now this is a perfectly fine sigma model that we can quantize. And we want to design a covariant background field method for it, which means we want to identify a covariant fracturation that we call C mu. And if you integrate all this C mu in the path integral, then in each line of your calculation, everything is fully covariant. So that will significantly simplify your quantum calculation. So to do that, let me note a little bit more ingredients about this string Newton-Galton geometry. So just like in GR, we designed these compatibility conditions, which says the covariant derivative of tau mu nu which is kind of like the longitudinal metric coming from tau mu A contracted with tau mu A. Set that to 0, and you also set this guy to 0. So E with lowered mu nu indices transformed not trivially under the boost symmetry, but with raised indices, it's a good quantity. It's actually invariant under the boost symmetry. And if you solve for these equations, we can get a Christoffel symbol, even though we don't have a metric field in the target space, but we do have a well-defined Christoffel symbol and hence a Riemannian tensor. But there's also, of course, ambiguity that it can introduce, which I'm not going to talk too much about it, but you can refer to Dieter's lectures for it. Finally, we can define this geodesic equation, just like in regular GR. And now we can identify this covariant quantum fracturation as a tangent vector that is tangent to the geodesic. And then if you expand x around x0 with respect to xi mu, so you'll be a Taylor expansion with respect to xi mu, and plug this back in the action and integrate out xi mu. After some pages of calculation that you can find in our papers, you'll land on this set of beta function nodes. So, and then at the end, if you set these beta function nodes to 0, that will give rise to the equations of motion in space-time, and that determine the dynamics of the string Newton-Garton geometry. So this will give rise to the notion of the so-called string Newton-Garton gravity. And let me re-emphasize that we're working in this zero winding sector. And this type of gravity just represents instantaneous Newtonian-like interactions. There's not really a graviton, as we discussed earlier. So it's in this sense, we have non-relativistic string theory describing as a UV-complete quantum gravity theory that is also non-relativistic. So I guess maybe, well, I'm already out of time. So I'll stop here for now, and tomorrow we'll be talking about the effective field theory on the deep brain, and also using it as a probe to discuss T-duality and S-duality in relativistic string theory. And at the end, we'll lead back to relativistic membrane theory, which is our starting point for the DLCQ of M theory. Okay, thank you.
Okay, thank you, Ziqi, for another good lecture.
Thanks, and I will stop recording for questions.
Okay.